Hello everyone and welcome back. In this lecture I will talk about race condition / reentrancy vulnerabilities in NEAR. Some people prefer to call them reentrancy, but I think race condition fits them better, so I'll be calling them race condition from now on. Alright, see you in the slide deck. Alright, so let's begin. Race condition might occur since there is a delay between the external call and the callback. Usually it's 2 blocks, and anyone can literally call any function inside of contract during this period. That person can call exactly the same function again or a totally different one. Like for instance, a smart contract stakes some NEAR to external contract, and before callback is executed, we just call withdraw function to withdraw all NEAR, but still we're gonna have some staked tokens in external contract. So we could either call exactly the same function or just any function in the contract during that delay period. And imagine a scenario where we have an external swapping contract which swaps NEAR to some tokens. And let's assume 1 NEAR equals 2 tokens. The user calls deposit function with 100 NEAR as attached deposit, and after this, user's internal NEAR balance increases. Then user calls swap NEAR function with 100 NEAR. That original contract calls external swapping contract with given amount and user account, and then swaps 100 NEAR for 200 tokens and increases user's internal balance inside of swapping contract to 200 tokens and returns promised success. Then after some delay, after 2 block delay, we get to resolve swap callback, and since promise was success, decrease NEAR balance is called to decrease user's balance to 0 since we spent all of our NEAR. And now user cannot just call swap NEAR function again since user does not have enough NEAR to swap tokens. So here's a diagram. Let's say Alice calls deposit with 100 NEAR, then Alice calls stake with 100 NEAR to get 200 tokens in external contract. Then smart contract calls external swapping contract to swap tokens. Swapping contract does everything and returns a promise back. And then callback is executed after 2 blocks to decrease Alice's balance to 0. So Alice cannot call stake again without calling deposit first. But what happens if we call swap function twice with 100 NEAR? So attacker calls that deposits 100 NEAR and calls swap function twice with 100 NEAR. So smart contract calls the external contract twice with given amount and user account. First, external contract will swap 100 NEAR for 200 tokens, increase user's external balance to 200 tokens and returns promise. Then external contract will swap 100 NEAR again for 200 tokens and increase user's balance in external contract now to 400 tokens since hacker already had 200 tokens from the previous swap. And then after 2 block delay, we get callbacks back. We get first callback to decrease attacker's balance to 0 since hacker spent 100 NEAR, so decreases NEAR balance is called, and now attacker's balance is 0. But then the second callback arrives and tries to do exactly the same thing, decrease attacker's balance to 0, basically by subtracting 100 NEAR. But since balance is already 0, we get panic on underflow. We cannot subtract 100 from 0. So due to delay in callback, attacker managed to stake 100 NEAR and get 400 tokens. We should have reverted any changes after we received panic or after we saw that attacker's balance is already 0. So here's the diagram. Hacker calls deposit 100 NEAR and then calls stake 2 times with 100 NEAR to get 400 tokens in external contract. And then hacker can just use external contract if, let's say, external contract has withdrawn, and just withdraw those 400 tokens and then swap them back to something else. And then smart contract calls external swap contract 2 times. External swap contract returns promise. And then first and second callbacks are executed after 2 blocks delay to decrease internal NEAR balance. So first callback is called and it's successful. Attacker's balance is decreased to 0 after callback. But the second one has failed because we cannot subtract 100 from 0 since attack already had 0 NEAR balance. But since we didn't revert any changes in external contract, attacker still has 400 tokens. Alright, so that's pretty much it for this slide deck. And I will jump into the code to show you an example in action and show you how we can just use integration tests to write our own POC. So, see ya. Hello everyone, welcome back to the code. In this example, we're going to try to exploit race condition in our victim contract. Again, you have access to victim contract, staking contract, and exploit contract in the race condition folder. So you can just navigate there to have access to them. This example is super similar to the one that I explained to you in the slide deck. Here we have just a deposit contract, which lets users to deposit some NEAR to then stake that NEAR in external contract. That's pretty much it. In the example, we had like external swapping contract. In this example, we just have external staking contract, which lets users to stake some NEAR under certain validator. And that's pretty much it. So to give you a quick walkthrough of the deposit contract, so we have just a new function. We have here just a user NEAR map that lets us track internal balances of users, and then we have staking contract address to make an external call. So we just initialize everything here. Then we have deposit NEAR that lets users deposit some NEAR. We just assert that attached deposit is bigger than or equal to 1 NEAR. Then we just have some if-else statements. If that's the first time user tries to deposit something, then we directly insert it inside of the map. And if user already had some money, we just basically add it on top. So we just have a current deposit plus the new deposit, and then we insert a new deposit to a user mapping. So then we have stake here, and we staking some NEAR for certain validator that user passes, and then we call the external staking contract to do that. So here we get just a NEAR deposit, and we ensure that user exists, and we check that amount is lower or equal to the NEAR deposit, so that user does not try to play the system. And then we're making an external call. So here we're just calling staking contract, and here is a trait for it. I'll show you this function in external staking contract afterwards. And here we can just give like beneficiary. Beneficiary is the caller of the staking function, so and validator that user passed and the amount. And then afterwards, after everything is done, we call a callback, call resolve staking. And here, if we get an error, we just panic and error from the call, external call. And if all good, we just log all good and then decrease the balance of the user. If user, for instance, deposits at 100 NEAR and then stakes 100 NEAR, we decrease user's balance to 0. So user cannot just call stake again without depositing anything. So here we just get user's NEAR deposit, then we create new deposit by subtracting whatever amount user staked from the current deposit. And then we add new deposit to a mapping update while updating the current deposit user has. So yeah, that's pretty much it. Also, we have some view functions such as like view NEAR deposit, and also we have withdraw NEAR here if user wants to withdraw NEAR without staking. That's pretty much it in this scenario. And let me move on to staking contract. In staking contract, we have allow list to only let deposit contract call stake, so that users cannot just call stake as they like in this contract. And here we have staking map to just keep track of users and balances, so that we can keep track. Let's say user A staked 100 tokens for validator B, something like this. So we have like user A, beneficiary, and we have validator and amount user staked. So we initialize everything in here. Then there is a staking function. We get caller. We check the allow list that to ensure that only deposit contract can call it. And then we just basically check if that's the first time user stakes, we just directly insert it into a contract, insert it into a mapping. And if it wasn't the first time, we just add on top. Basically, we get current stake for a certain validator, and then we add amount on top. And then we have withdraw stake. And withdraw stake just lets users to withdraw stake from a validator. So we ensure that amount that user tries to withdraw is not zero. Then we check that beneficiary stake, that stake actually exists. And then we ensure that beneficiary stake is bigger or equal to amount so that user cannot play the system. And then we just subtract the amount from the beneficiary stake and update current mapping. And then we just log everything and send near back to a user, whatever amount user withdrawn. And then we have also view stake function to view current stake of a user. That's pretty much it for exploitable contracts. We could exploit it like in two ways. I will show you both. We could just use exploit contract to call it and just let it do automatically, or we could just use workspace as our Rust integration tests batch function to batch two stake calls and just make everything work in that way. So let me just show you the exploit contract first, because we're going to be doing it in both ways. So in exploit contract, we have just vulnerable contract trait in here. We have stake, so its stake comes from the deposit from here. And then we just initialize the defaults, and there is like exploit function that exploits everything. And here we are calling just a stake function inside of the deposit contract, and then using AND keyword to make it basically do it at the same time, literally. So, and then we call stake again, and then afterwards we just, to have like a better, let's say, logging experience and to understand whether everything was okay, we just call resolve exploit, and here we just check if it was error. We just call back error with an error, and then here we just log callback succeeded. That's pretty much it in this scenario. And let me move on to integration tests. So we have exploit race condition here. We're obviously, as usual, we're going to have prepare race condition. We just deploy every single contract and initialize them. And let me move on to race condition. Here we call just deposit contract deposit near, and we deposit 20 near, as you can see from here. So 1 near times 20. And then we just assert that everything worked well, everything is success, and then we just print some logs. So here we're gonna be using the exploit contract. So we're gonna call exploit from here, exploit function to exploit this race condition, and we're adding address of deposit contract and amount that we want to use for staking, which is like deposit amount, which is 20 near. But in this scenario, since we're calling it twice, it's going to be 40 near. And we assert that we actually have failures. It might sound weird, but since we, at the end of the day, going to get panic on subtraction with underflow. So let me show you here. Since, as you know, if we call stake twice, let me just find it. Yeah. So if we call stake twice, as in the example I explained to you in the slide deck, we're first going to get a first callback. So let's say we deposit 100 here and we call stake twice. So first callback gets resolved in here, and we reach decrease balance function, and user's balance going to get decreased from 100 near to 0 near, since user deposit 100 near and staked also 100 near. So 100 minus 100 is 0. So we're going to insert the user's balance as 0. But then afterwards, the second callback is going to arrive, since we called stake twice. And in this scenario, we're also going to get like all good, and we're also going to reach decrease balance. But in this scenario, since user's balance already 0, we're going to get panic subtract with underflow, so it's going to be an error. But like the main issue, we're not reverting anything in here, so user will still have 14 year in the staking contract in here. So that's why we're ensuring that there are actually errors in here. And we also want to get exact error that's happening. So we know that's all good. If that's the error that we're getting, all good, continue. So we just basically iterate over failures, and we check if any error is smart contract panic subtract underflow. That's pretty much it. And then we just check if that's correct. And then we move to basically getting stake amount from the external contract, external staking contract. We just literally call the view stake from here to get user stake. And in this scenario, we expect user staked amount to be deposit amount times 2, basically 20, because we called the exploit twice, so basically deposit amount times 2. So we expect user to have 14 year in the staking contract. And then we just print the staking contract. And then we get exploit contracts balance, because at the end of the day, what we try to do is to withdraw that stake, withdraw extra money. So let me get exploit contract balance before. We just print it out. Then we're gonna call withdraw stake with validated test near, because we use test near to deposit it, and withdraw 40 near. And then we just assert that everything works and print logs. And then we also gonna get a new balance back after withdrawing funds. And then we're just gonna print it out also. So that we can see from prints how balance is changing. And then we afterwards getting staked amount again, and we assert that staked amount now is 0 since we withdraw all the funds, and then we just print the staked amount. So that's pretty much it for the exploit. So let me run it to show you how it works. Just make it bigger. Okay, so we're deploying contracts. As you can see from here, we deposited 20 near. Now staked amount is 14 year. Okay, exploit contracts balance before withdraw is this amount. Then we transferred 14 year, and then exploit contract balance after withdraw is this. So it's basically just this value plus this value, and also some gas fees. And then afterwards we have staked amount 0 to check that we actually withdrew everything, and everything is correct. Our exploit works, and we managed to get extra 20 years, so isn't that good? So let me show you the second way you can exploit this is to use just batch calls from the workspaces near. If you I don't know, if you're too lazy to write your own exploit contract. Okay, let me just comment this out, uncomment those lines out. So let me save everything. So what we do here, we just call exploit contract as account, then we create batch call to call the deposit contracts stake function. We use validated test near and amount, deposit amount, and we'll literally just also specify some gas, so it all passes. And then we chain another call with exactly the same arguments in here, and then we just transact and await. And then everything should work as expected in exactly the same way we use exploit contract. So let me just run it. All contracts are getting deployed. We deposited 20 near. Balance before withdraw, so we would actually manage to stake 14 year. Exploit contract balance before withdrawn 14 year. Exploit contract balance after withdraw, so it increased, and then staked amount is 0, so we actually managed to withdraw everything. So all right, exploit works, and that's amazing. Now we know how we can exploit those scenarios. So that's pretty much it for this video, and I see you in the next lecture.